In the darkening skies over the Pacific in early 1945, American sailors watched with growing dread as Japanese aircraft dove toward their ships with deadly intent. These weren't ordinary attacks. The pilots had no intention of pulling out, no plans to return home. They were kamikaze, the divine wind, and they were changing the nature of naval warfare in ways that terrified even the most battle-hardened veterans. But what the Japanese High Command didn't know was that American intelligence officers and engineers had been quietly studying every captured aircraft they could get their hands on, and what they discovered would ultimately turn the tide against this desperate new tactic. The story begins not with the kamikaze attacks themselves, but several years earlier, in the early days of the Pacific War. When Japan launched its surprise assault on Pearl Harbor in December 1941, American military planners were shocked not just by the audacity of the attack, but by the performance of Japanese aircraft. The Mitsubishi Zero fighter had become a legend almost overnight, shooting down Allied planes with seeming ease, outmaneuvering everything the Americans could put in the sky. Pilots reported with frustration that the Zero could turn tighter, climb faster, and fly farther than any American fighter. It seemed almost supernatural in its capabilities. But there was a problem with understanding this mysterious aircraft. American intelligence had very little concrete information about how it actually worked. Prior to the war, Colonel Claire Chennault, commander of the Volunteer Flying Tigers in China, had sent detailed reports to the United States Army Air Corps warning them about this fast, highly maneuverable fighter plane the Japanese had developed. His letter, however, had apparently been buried in a filing cabinet and forgotten. The prevailing attitude among American military analysts was one of dismissal. When presented with performance reports about the Zero, Department of War analysts actually rejected them as impossible, literally calling them nonsense. The numbers, they said, were aerodynamically impossible. How could the Japanese, whom they had underestimated so thoroughly, build something so advanced? This dangerous underestimation cost American lives in the early months of the war. Pilots went up against Zeros with tactics designed for slower, less maneuverable opponents, and they paid a terrible price. The Zero seemed to dominate every engagement, shooting down American aircraft at alarming rates. Something had to be done, but first, the Americans needed to understand their enemy. The breakthrough came on June 4, 1942, during the Japanese diversionary attack on the Aleutian Islands. While the main Japanese force moved toward Midway Island in the Central Pacific, a smaller flotilla struck at American installations in Alaska, specifically targeting Dutch Harbor. The attack was fierce. Japanese bombers and Zero fighters strafed the base, and American anti-aircraft batteries filled the sky with fire. During the chaos of the second day's attack, one Zero fighter took hits. Bullets punctured the fuel line of the aircraft piloted by Flight Petty Officer Tadayoshi Koga. With fuel streaming from his damaged plane, Koga radioed his flight commander. He would attempt an emergency landing on Akutan Island, a small piece of land that had been designated as the backup location for disabled aircraft. As Koga approached the island minutes later, he lowered his landing gear and made his final approach. But Akutan Island, like much of the Aleutians, was treacherous. The landscape was covered with grassy marshes that looked solid from the air, but were anything but. Koga's wheels touched down on what he thought was firm ground. Instead, they sank immediately into soft, waterlogged earth. The Zero flipped violently onto its back. The impact was catastrophic. Koga's neck snapped instantly, taking his life in a fraction of a second. His wingmen, circling overhead, hoped he had survived and, following protocol, did not destroy the downed aircraft as they normally would have. The Japanese carriers, anxious to withdraw after the attack, apparently made no attempt to locate the missing pilot or his plane. The Zero lay there in the Aleutian Marsh, relatively intact, for 5 weeks. When an American Navy Catalina seaplane finally spotted the wreckage in mid-July, the crew could hardly believe their eyes. Here, sitting in an Alaskan bog, was one of the most sought-after intelligence prizes of the entire war, an intact modern Zero fighter. When the salvage team finally reached the crash site, they realized immediately the magnitude of what they had found. This wasn't just a crashed enemy plane. This was the key to understanding Japan's air superiority. The recovery operation was an ordeal. For more than a month, multiple teams struggled through knee-deep mud, working to extract the aircraft without causing further damage. The Zero was disassembled piece by piece, each component carefully documented and packed. Finally, the crated aircraft was shipped across thousands of miles of ocean to Naval Air Station North Island in San Diego, California. What happened next would change the course of the air war in the Pacific. American aviation experts descended on the captured Zero with an intensity rarely seen in military history. Every rivet, every structural member, every control surface was examined with meticulous care. The aircraft was reassembled with precision, and preparations were made for the most important part of the evaluation, flight testing. On September 20th, 1942, Lieutenant Commander Eddie Sanders climbed into the cockpit of the Akutan Zero. The engine roared to life, and for the first time, an American pilot would experience firsthand what made this fighter so formidable. Over the next several weeks, Sanders made 24 test flights. Each flight was carefully planned to explore different aspects of the Zero's performance. And with each flight, the mystery began to unravel. The results were revelatory. Sanders and the team of engineers discovered that the Zero was, in many ways, exactly as advertised. Its maneuverability was extraordinary. The aircraft could turn on what seemed like an impossibly tight radius. Its rate of roll to the left was impressive, aided by the torque of its powerful propeller. The range was phenomenal for a carrier-based fighter. These were the qualities that had made it so deadly in the hands of skilled Japanese pilots. But the testing also exposed something the Japanese had hoped the Allies would never discover. The Zero had critical weaknesses, deep, exploitable vulnerabilities that could be turned into tactical advantages. First, and most shocking, was the aircraft's structural fragility. Chief designer Jiro Horikoshi had created the Zero with one overriding principle: weight reduction. To achieve the performance requirements demanded by the Imperial Japanese Navy, particularly the incredible range needed to escort bombers deep into China, Horikoshi had to make the aircraft as light as possible. He accomplished this through revolutionary techniques for the time. Lightning holes were drilled and cut through every internal airframe component where structure could be reduced. The technique was similar to what race car builders would later use, and it worked. But it came at a terrible cost. When American engineers examined the Zero's structure, they were astounded by how thin everything was. One traditional Japanese engineer, when asked after the war to identify the Zero's main weakness, complained bitterly that the aircraft was full of holes. The reduced structure meant the Zero had multiple single-point failure modes. One well-placed bullet could cause catastrophic structural failure. The aircraft had no armor plating to protect the pilot, none. American pilots had reported that Zeros seemed to disintegrate or burst into flames after sustaining what should have been minor damage, and now the engineers understood why. Even more critically, the Zero lacked self-sealing fuel tanks. This was a technology the Americans had developed and implemented across their fighter fleet. Self-sealing tanks had internal bladders that would swell and close off holes when punctured, preventing fuel from streaming out and igniting. The Zero's tanks were conventional. A single tracer round through a fuel tank could turn the entire aircraft into a fireball. American flyers had taken to calling them flying Zippos, and the examination of the captured Zero confirmed why. The aircraft was, quite literally, a flying tinderbox. The flight testing revealed even more tactical weaknesses. Sanders discovered that while the Zero was unbeatable in a slow-speed turning fight, its performance degraded dramatically under certain conditions. At speeds above 260 miles per hour, the Zero's controls became heavy and unresponsive. The aircraft lost its legendary maneuverability. This was critical intelligence. American fighters like the Grumman Wildcat might not be able to outturn a Zero, but they could fly faster. During high-speed dives, the situation became even worse for the Zero. The aircraft couldn't maintain a steep dive. Structural stress and control issues meant Japanese pilots had to be cautious when diving. American fighters, built with more robust airframes, had no such limitations. They could dive away from trouble at speeds the Zero simply couldn't match. Perhaps most exploitable was the Zero's asymmetric roll performance. The large propeller generated enormous torque. This meant the aircraft could roll quickly to the left, but rolling to the right was significantly slower. A skilled American pilot who knew this could shake a pursuing Zero by braking hard to the right. The Japanese pilot would struggle to follow, his aircraft fighting against its own design. The data from the captured Zero was immediately distributed to American fighter squadrons across the Pacific. Tactical bulletins went out explaining how to fight the Zero. Don't try to dogfight. Don't get into a turning contest. Instead, use speed, hit fast, hit hard, and get out. Make slashing attacks from above using superior diving speed. If caught in a disadvantageous position, dive away to the right. Keep your speed up, and the Zero can't follow. Commander John Thatch had already begun developing innovative tactics based on combat experience. His famous Thatch Weave, where two fighters would cross paths and cover each other, proved devastatingly effective against Zeros. Now, with concrete data from the captured aircraft, these tactics could be refined and taught systematically. But the intelligence coup went far beyond tactical advice. The data was sent to Grumman Aircraft, the company building America's carrier-based fighters. Roy Grumman and his team studied every detail of the Zero's performance. They realized they could design an aircraft that would match or exceed the Zero in almost every category, except range. The key was to not try to beat the Zero at its own game. Instead, they would build a fighter that prioritized what the Zero lacked: protection, firepower, and raw power. The result was the Grumman F-6F Hellcat. Where the Zero sacrificed everything for maneuverability and range, the Hellcat was designed around survivability and performance at high speed. It had armor protection for the pilot, self-sealing fuel tanks, rugged construction that could absorb battle damage, and most importantly, a massive 18-cylinder Pratt & Whitney engine producing over 2,000 horsepower, more than double what powered the Zero. The impact was dramatic. When the Hellcat entered service in 1943, the air war began to turn. American pilots now had an aircraft that could compete with and ultimately dominate the Zero. The kill ratios shifted dramatically in America's favor. By the time of the Great Marianas Turkey Shoot in June 1944, American pilots and anti-aircraft gunners shot down over 500 Japanese aircraft for the loss of just 123 American planes. The myth of Zero invincibility was thoroughly shattered. Admiral William Leonard, himself a fighter ace, would later say that no other captured machine had ever unlocked so many secrets at a time when the need was so great. The Yakuten Zero, as it became known, had quite literally saved countless American lives and changed the trajectory of the air war. But the story of American engineers examining Japanese aircraft doesn't end with the Zero. As the war progressed and Japan's situation became increasingly desperate, the aircraft the Americans captured and examined revealed an enemy in the throes of industrial collapse and mounting desperation. By October 1944, Japan had suffered catastrophic losses at the Battle of Leyte Gulf. The Imperial Japanese Navy had ceased to be a viable fighting force. Most of their experienced pilots were gone, taken by the relentless attrition of combat. Their industrial capacity was being systematically destroyed by American bombing raids. Raw materials were in critically short supply due to the Allied naval blockade, and the Allies were closing in on the Japanese home islands themselves. In this desperate context, the Kamikaze was born. Vice Admiral Takejiro Onoshi, newly appointed commander of the 1st Air Fleet, proposed a radical solution. If conventional bombing attacks were becoming less effective as pilot quality declined, why not turn the aircraft itself into the weapon? A novice pilot could fly an aircraft into a ship far more easily than he could accurately drop a bomb on it, and the sheer momentum of a crashing plane, even one that was damaged and burning, would often carry it to its target long after the pilot had been struck. The first organized kamikaze attacks were launched from the Philippines in late October 1944. The results were shocking. On October 25th and 26th, coordinated kamikaze strikes sank the escort carrier St. Lo and damaged several other ships. The psychological impact was immediate and profound. Sailors who had faced conventional air attacks now confronted something entirely different. Pilots who were willing to give their lives, who couldn't be deterred by the prospect of being shot down because being shot down was the mission. American intelligence officers and technical specialists began recovering debris and studying kamikaze aircraft whenever possible. What they found painted a picture of an enemy aviation industry in crisis. Early kamikaze attacks had used conventional fighters and bombers, many of them well-maintained aircraft flown by skilled pilots who volunteered for the missions. But as the campaign continued, the quality of both the aircraft and the pilots declined precipitously. Specialized kamikaze aircraft began to appear, and American technical teams were horrified by what they found. The Yokosuka MXY-7 Oka, which American sailors mockingly called the Baka bomb, was essentially a rocket-powered flying bomb with a human guidance system. The Oka was a wooden aircraft with a 1,200-kilogram warhead and 3 solid-fuel rocket motors. It had to be carried under a Mitsubishi Betty bomber and released within range of Allied ships. When American engineers examined captured Oka aircraft after the war, they found the design both ingenious and terrifying. The aircraft could achieve extraordinary speed once the rockets fired, making it extremely difficult to shoot down in the final dive. But it had a fatal weakness. The Betty bombers carrying the Okas were slow, heavily loaded, and vulnerable to fighter attack. American combat air patrols quickly learned to target the motherships before they could release their deadly cargo. Of 300 Okas prepared for the Okinawa campaign, only 74 actually launched, and many of those were destroyed with their parent aircraft. But it was the truly desperate measures that revealed just how dire Japan's situation had become. In 1945, American technical intelligence teams began encountering aircraft that shocked even veteran engineers. The Nakajima Ki-115 Tsurugi was designed specifically as a disposable kamikaze aircraft. The specifications were chilling. It had to be cheap and easy to build. It had to use non-strategic materials. And critically, it was designed to never land. The landing gear was jettisonable, meant to be dropped after takeoff. There was no need for retractable gear on an aircraft that would never return. Engineer Aori Kunihiro led the design team, and they created something that was less an aircraft and more a flying projectile. The fuselage cross-section was circular, not elliptical, because it was easier to manufacture. The engine could be any power plant available from Japan's dwindling stocks, even obsolete engines from the 1920s and 30s. The instruments were minimal, the controls were crude, and the performance was abysmal. When American forces captured Ki-115s in various stages of completion after the war, the examining engineers were struck by the aircraft's shortcomings. It had terrible takeoff and landing characteristics. The visibility from the cockpit was poor. Only experienced pilots could fly it safely, which defeated its purpose of being piloted by minimally trained volunteers. Several test pilots had perished in crashes during the Japanese testing program. The aircraft was a death trap, and not in the way its designers intended. Even more shocking was the Tago, designed by Captain Yoshiyuki Mizuyama. When American engineers examined this aircraft, they could scarcely believe what they were seeing. The Tago was an attempt to create a kamikaze aircraft that could be built in small workshops across Japan using almost no strategic materials. The final version had a tiny four-cylinder engine producing just 110 horsepower, driving a wooden propeller. The construction was almost entirely wood and fabric. The pilot sat in an open cockpit with only a small windshield. The entire aircraft weighed less than 1,300 pounds fully loaded, including a small bomb attached underneath. The Tago had a top speed of 120 miles per hour and a range of 93 miles. In the skies over Okinawa, where American combat air patrols consisted of powerful fighters like the Hellcat and Corsair, a Tago would have been little more than a flying target. But the Japanese were planning to build them by the thousands, hoping that sheer numbers might overwhelm Allied defenses. American intelligence teams also discovered evidence of even more desperate measures. Training aircraft, some of them wood and fabric biplanes dating back to the 1930s, were being converted for kamikaze use. The Yokosuka K-5Y, a basic trainer with a top speed barely over 100 miles per hour, was pressed into service. The last American ship sunk in the war, the destroyer Callahan, was struck by one of these obsolete biplanes. It was a sobering reminder that even the most primitive aircraft, when used as a guided missile, could be deadly. What made these discoveries even more significant was what they revealed about Japanese aircraft construction quality in the final year of the war. Maintenance records and technical drawings captured at Japanese facilities showed a systematic decline in build quality. Precision tolerances were being relaxed. Substitute materials of inferior quality were being used. Quality control procedures were being shortened or skipped entirely to increase production rates. American engineers examining Japanese aircraft captured on Saipan, Iwo Jima, and Okinawa found extensive evidence of this decline. Engine components showed poor machining. Electrical systems were increasingly unreliable. Structural joints that should have been precisely fitted showed gaps and misalignment. Even frontline fighters, not just kamikaze aircraft, were affected. This had direct implications for the kamikaze threat. Even when relatively modern aircraft were used for attacks, mechanical failures were becoming increasingly common. Engines failed to start. Landing gear wouldn't retract, creating drag that limited range. Fuel systems leaked. Navigation equipment malfunctioned. Many kamikaze formations were depleted by mechanical issues long before they reached Allied ships. The Americans also discovered extensive files on Japanese technical intelligence efforts. The Japanese had been studying captured Allied aircraft throughout the war, just as the Americans had been studying Japanese planes. At facilities like the Army's Aviation Technical Research Institute at Tachikawa and the Navy's 1st Air Technical Research Arsenal at Yokosuka, Japanese engineers had examined B-17 Flying Fortresses, P-40 Warhawks, F-6F Hellcats, and numerous other American and Allied aircraft. But the comparison between American and Japanese technical intelligence efforts was revealing. The Japanese were impressed by American aircraft, particularly by their subsystems and pilot protection features. Designer Kikuhara Shizuo noted how American aircraft like the B-17 had perfected subsystems to the point where minimal cockpit controls were needed. When Japanese engineers examined a captured F-4U Corsair, they were surprised to find fabric coverings on portions of the wings alongside metal construction. They admired the extremely strong construction of the Grumman Avenger. But Japanese engineers were hobbled by their own industrial limitations. They couldn't simply copy the features they admired. Japan lacked the high-grade alloys that made American engines so powerful and reliable. They didn't have the manufacturing capacity to build self-sealing fuel tanks in quantity. They couldn't match American production techniques that allowed for both quality and quantity. The very things they learned from studying American aircraft only highlighted how far behind they had fallen. As the war moved into its final months, American defensive measures against kamikaze attacks became increasingly sophisticated. The captured aircraft data played a crucial role in developing these countermeasures. Engineers understood the limitations of the aircraft being used against them. They knew the performance envelopes, the structural weaknesses, the vulnerabilities. This knowledge informed the development of new tactics and technologies. Radar picket destroyers were stationed far from the main fleet to provide early warning. Combat air patrols were enlarged and positioned farther out, giving fighters more time to intercept incoming attacks. Anti-aircraft batteries were coordinated more effectively. Gun directors were trained to target the most vulnerable parts of attacking aircraft based on captured examples. The Americans also developed what became known as the Big Blue Blanket strategy. This involved maintaining continuous fighter coverage over Allied fleets around the clock, with multiple layers of defense. Japanese aircraft attempting to reach the fleet had to penetrate multiple defensive zones, each one taking a toll. By the time they reached the ships themselves, their numbers had been drastically reduced. The intelligence gained from examining kamikaze aircraft also revealed Japanese plans for defending the home islands. American forces captured documentation and partially constructed aircraft that painted a chilling picture. The Japanese were planning to use thousands of kamikaze aircraft against the expected Allied invasion. These wouldn't just be conventional planes converted to one-way missions. There were purpose-built designs, some of them jet-powered, that existed in various stages of development. The Nakajima Kika, Japan's only jet-powered aircraft to actually fly during the war, made its first flight on August 7, 1945. It was loosely based on the German Messerschmitt 262, but smaller and with folding wings designed to allow it to be hidden in caves. American intelligence officers examining the design after the war realized it was intended for use in kamikaze attacks against the invasion fleet. With a top speed of over 400 miles per hour, it would have been far more difficult to intercept than the obsolete trainers and Kai-115s. Even more advanced designs were in development. The Kyushu J-7W Shinden was a radical pusher configuration fighter with the engine behind the pilot driving a 6-bladed propeller. It had an estimated top speed of 466 miles per hour. 2 prototypes were completed and one made its first flight on August 3, 1945, just days before the war ended. A jet-powered version was being planned. American engineers examining the Shinden were impressed by the innovative design, even as they were relieved it had never entered production. The intelligence picture that emerged from all these captured aircraft was sobering. Yes, Japanese aviation was collapsing under the weight of material shortages and industrial bombing. Yes, the quality of aircraft and pilots was declining precipitously, but Japan was also prepared to throw everything it had at an invasion force. The Americans estimated that over 12,000 aircraft, including thousands of kamikazes, were being held in reserve for the defense of the home islands. Many were hidden in caves under camouflage, in small workshops. They would have been launched in massive waves, attempting to overwhelm defenses through sheer numbers. When the atomic bombs were dropped on Hiroshima and Nagasaki in August 1945, ending the war, one of the often overlooked consequences was that it prevented what would have been the largest kamikaze operation in history. American sailors and the technical intelligence officers who had studied Japanese aircraft extensively understood just how close they had come to facing an aerial assault of unprecedented scale. The captured Japanese aircraft that American engineers examined throughout the war from the first intact Zero found on Akutan Island to the desperate kamikaze designs discovered after Japan's surrender, told a story that went far beyond simple technical specifications. They revealed a nation that had started the war with some of the world's most advanced naval aviation, only to see that advantage slowly eroded by industrial capacity, resource limitations, and the terrible mathematics of attrition warfare. The weaknesses found in Japanese aircraft, particularly the kamikaze planes, were not just engineering flaws. They were symptoms of a larger collapse. The lack of armor and self-sealing tanks that made the Zero so vulnerable stemmed from Japan's need to maximize range to compensate for limited carrier capability. The crude construction of late-war kamikaze aircraft reflected a nation running out of aluminum, steel, and skilled workers. The desperate tactics reflected a military that had lost most of its experienced pilots and couldn't train replacements to the same standard. But perhaps most importantly, the examination of these aircraft by American engineers demonstrated the crucial role of technical intelligence in modern warfare. The Akutan Zero alone provided information that saved countless lives and accelerated American air superiority. The subsequent analysis of kamikaze aircraft allowed for effective countermeasures that reduced their impact. Understanding the enemy's capabilities, down to the nuts and bolts level, proved as important as any weapon system. In the decades after the war, historians and engineers continued to study the Japanese aircraft of World War II. The Zero, despite its vulnerabilities, is still recognized as one of the most influential fighter designs of its era. Its combination of range, maneuverability, and simplicity influenced post-war aviation. The kamikaze aircraft, crude as many of them were, represented an early form of precision-guided munition foreshadowing modern weapon systems. Today, some of these aircraft survive in museums around the world. The Akutan Zero itself was destroyed in a training accident in 1945, but other examples of Japanese aircraft, including kamikaze types, are preserved. They stand as reminders of a time when American engineers and intelligence officers, working under intense pressure and with limited resources, managed to uncover the secrets that helped win a war. The crews who salvaged the Akutan Zero from that Aleutian marsh, the engineers who spent countless hours examining its structure, the test pilots who flew it and documented its every characteristic, the intelligence officers who distributed the findings, and the designers who used that information to create better American aircraft, all played crucial roles in the outcome of the Pacific War. Their work examining enemy aircraft piece by piece, rivet by rivet, discovering weaknesses and exploiting them, represents one of the most successful technical intelligence operations in military history, and in the end, the shocking weaknesses they uncovered in Japanese kamikaze planes revealed not just flaws in aircraft design, but the fundamental limitations of a strategy born of desperation. No amount of willingness to make the ultimate effort could compensate for inferior materials, declining construction quality, inadequate pilot training, and aircraft that were increasingly outmatched by their opponents. The divine wind that the kamikaze were named for had once saved Japan from invasion. But in the skies of 1945, American fighters and anti-aircraft fire proved to be the stronger force, and the intelligence gained from examining captured Japanese aircraft had shown them exactly where to strike.